Welcome to part 4 in the 10 things you need to know about infrared windows webinar series. This webinar is going to deal with a very important subject, that of the infrared window transmission rate. What affects it and how do you calculate it. So again, we went through the infrared materials in part 2, and we looked, what we've seen there was every material has its own unique transmission curve. And where we work in, again, where we went through particularly, is in the long wave infrared wavelength, in particularly again between 8.5 and 9.5 microns. So what we're going to sort of discuss in a little bit more detail is how these curves behave differently in different workplace and environmental situations. So let's look at how infrared energy transmits through an infrared window. Now we know infrared energy transmits from any object above absolute zero. So what we do is we have infrared energy transmitting through an infrared window, and the environmental factors concerning that can actually affect the transmission. If it's hygroscopic, it can absorb water. High frequency noise and vibration can cause micro cracking, which can accelerate the absorption of those water, acids, alkalis and water in the atmosphere, humidity. So again, what we end up with is, with all of these contributing factors, what is the actual transmission rate of an infrared window? If the materials like the fluoride-based materials are hygroscopic and susceptible to high frequency noise and vibration, their transmission rate can change at an unknown rate. We've had them fail in as little as 10, 11 months, where some have gone on for several years. So it's a really unknown, but it's a fact that these things do change over time, and it's working out what that change is very important. So you can check your infrared optic routinely, and that with electrical panels, basically when we shut them down for a housekeeping service, which maybe every 5 years, depending on the operation. I've had some operations that do a shutdown every year just to clean out the panels. We need to look at how we are going to maintain our infrared windows or service our infrared windows. So cleaning is important. Obviously, if it's like any window, they'll get dirty. So if you can clean them, with water, dry cloth, detergents, etc. Get your cleaning agent sorted out before the shutdown, and plan this in. Write this into your servicing schedule, that the infrared windows need to be cleaned, how they need to be cleaned and dried, etc. If there's any repairs that need requiring, so if the doors have been hit, the gaskets have been torn, these are like anything, they can be serviced. So again, if there is any servicing requirements, make a note of it, because you need to service them during the shutdown. And the final most important thing is completing an infrared transmission check. Now we already know, as we've gone through many times, that the fluorides will change over time. Now, unlike the fluorides, polymers don't change. They're quite a stable material, so that we have what we call FAST, the fixed and stable transmission rate. But you can check, if you, for instance, you may have had new cameras or whatever, you can check the transmission rate of any infrared window system you have, and we use a method called the coffee cup test. So what the coffee cup test is, basically a simple way of checking the infrared transmission rate of your infrared window. It should be completed when they're new, during the installation, so you know what the transmission rate is with your camera, because we've already gone through how different cameras have different transmission rates. But as long as the material doesn't change, the transmission of the material doesn't change, then the transmission rate won't change. Well, this video is going to show just how we can compensate for an infrared window using infrared window transmittance, a bit like the coffee cup test, what we call in Iris. So if you look at the image now, what you can see is a viewfinder of the camera. I'm looking at a black body, but this could be any hot surface, such as a cup of coffee, etc., with a known emissivity. So I'm looking at this now, and my peak temperature in the area is 101 degrees. So if I put the infrared window in front of the camera, you'll see that goes from 101 to 87.8. So that is transmission loss, and what I'm trying to do is account for that transmission loss. Okay, so if I look through the infrared window, don't forget we're trying to get to 101 degrees. If in this camera I can go by going to object parameters this does have an external optics setting. If I switch that on, I can now start to change or bring that down, and notice as I bring that down, the apparent temperature starts to increase. Now I'm bringing that down until I see about 101 degrees. Okay, so I'm dropping, gone slightly past it, come back up, come back down. 101 degrees is a 59, this means this infrared window system has a 59% transmission. If I set that, then every time I want to use an infrared window, I would switch on this transmission setting and set it to 0.59. If I don't switch it off, you can see that that temperature now is 121. So by going into the external optics transmission and taking it back to 1, which basically is zero window, you can see it's back to 101. So here we can see that the infrared transmission for using this infrared window, the VPT clear polymer window, is basically 59% with this camera. So again, just to review the coffee cup test, you can get a warm target. I mean, in the video I use the black body, but you know, typically a cup of coffee, etc. Place a target with known emissivity on the surface of the cup. Black electrical tape is something that is used many times for this. Measure the temperature of the tape without the IR window and record the temperature. Then place the IR window in front of the camera and complete the exercise again, recording the temperature. Then using either the camera or your reporting software, change the transmission rate as I did in the video, till those temperatures match. When I say match, you know what the transmission rate is, and you can record that transmission rate on the IR window label or in the report template for future use. So a very simple test to do, but a very important test. So when you're looking at compensating for transmission loss, I would say the vast majority of new infrared cameras have an external optics or IR window compensation setting. Now when you look at, unfortunately, your older cameras or low cost entry cameras do not have the ability to offset for transmission losses using this external optics compensation or infrared window compensation setting. However, for a quick check in the field, you can use the emissivity of the setting to help you out in this. You can multiply the transmission rate of the infrared window with the emissivity of the target. So this is why it's always important that you know the emissivity of the target. So use the emissivity and multiply that transmission rate, and you'll get a good apparent temperature. So in this instance, when we had the transmission rate, we know the transmission rate is 59% on this window, and at 9 microns, measuring a target with an emissivity of 0.95, a bit of electrical tape, would require the emissivity to be set to 0.56, because what I would do is multiply 0.9 by 0.59, 0.95 sorry, by 0.59, and I'll get 0.56. So quick check will allow you to estimate the temperature of the target on the other side of the window. So if you've got a camera, no window setting, use the emissivity, multiply the emissivity of the target. So you might have to guess the emissivity of the target if it hasn't been predetermined by a label or tape, etc. But for instance, if you were looking at a cable gland or a cable joint where you go back to the cable sheathing, which is approximately 0.95, that's a good way to work out what the apparent temperature is of your target. Now again, when you look at the curve, if you see this curve here, this graph shows how readings can, like for instance with the emissivity settings what we went through in part 3, if your emissivity is too low, your calculated temperature is too high, and the same is with transmission rate. And if you look at this graph, it shows 11.8 degrees Celsius rise between 1 and 0.5 on the transmission rate. That's a 30% change. Now, think about what we went through in part 3 of this series when we went through emissivity. Emissivity has very similar characteristics. So if your emissivity is wrong and your transmission rate is wrong, or your transmission rate is changing and you're calculating it wrong, you're going to have some real significant differences in the actual versus the apparent temperature of your target. So be very careful and be very aware just how important these things are. If you look at when we went through the infrared window materials, you can see here, just looking at the materials at the same target, we have a calcium fluoride lens of 33% loss and the polymers with 22 to 23% loss. So again, very significant measurements, and when you're using temperature as your repair criteria, you really need to make sure your temperature measurements are solid and you understand just how much transmission and the emissivity can affect these readings. So, summary. Know the characteristics of the infrared window optic as it pertains to your infrared camera. Okay? Check the infrared transmittance and document the results. Compensate for the transmission attenuation or losses for the accurate temperature measurements of the components within your panels. Always retest crystal infrared transmission rates as they are known to change over time, and include all IR windows in general maintenance of the equipment in which they are fitted. So thank you for attending this webinar. If you need any more information regarding transmission rates of infrared windows and different materials, or anything to do with electrical maintenance safety devices, please visit our website at www.iris.com.